All right, time for us to tackle some problems involving mass and center of mass. As always, it's important that you do many problems as you can on your own, because that's the way, as a bodybuilder might say, to build up your mass, right? Yes. Another way to put it, you gotta do the reps. Take the time and develop your skills. So if you're following along with the video, make use of the pause button. See a problem? Pause it. See if you can figure it out. Pretty soon, you're going to be doing all sorts of amazing problems, and you're going to be learning all sorts of wonderful calculus things. So, without any further ado, let's begin. Our first problem. Find y bar for the constant density region where y goes between sine x and cosine x, and x goes from negative pi over 4 to pi over 4. Now, whenever you see something that says constant density, and it doesn't tell you what the density is, then what you should say is, well, it doesn't really matter. Because if you just increase your density of a region, well, you scale the mass by the same amount. So if you double the density, double the mass. But if you double the density, it doesn't change your center of mass. So that's why it doesn't really need to specify. So as a rule of thumb, if they say constant density, just think the density is 1. Just makes it very simple to work with. And recall, what is y bar? Well, that's the y-coordinate for the center of mass, which is the moment divided by the mass. All right, and it's that really strange thing, right? That y bar requires the moment with respect to x. Okay, well, let's think about our current problem. So if we sketch this, it's not so bad to sketch. We can sketch our two curves, and what do we see? Well, sine of x looks something like this, whereas cosine of x will do something more like that. Now, where are we going from? We're going from negative pi over 4 to positive pi over 4. In terms of the picture, pi over 4, that's actually at this intersection point. Negative pi over 4 is over here. So that's the shape of our region. Okay, so there's our region, and we're after the question, where's the y-coordinate for the center of mass? Now we begin. Okay, so let's start with, well, the mass, right? We've got to start with one of them. Might as well start with mass. It doesn't really make a difference which one we start with. So how do we do mass? So the way we find mass is it's the adding up of the little pieces of mass. So from A to B. And since it's two-dimensional, we think of it as we have a density times an area. And an area is a height and a width. Okay, so that's our very generic formula. So we're thinking of mass in 2D. That's where we start. So, what's our density? 1. Because that's what we said it is. Density is 1. Perfect. Perfect. Our width, well, we're going to slice. We have to think about how we slice it. I mean, do we slice vertically or horizontally? Well, everything is given to us as functions of x. So we're going to integrate with respect to x, and that means that we're slicing vertically, like dx, small change in x's. So that's vertical slices. So that's dx, which means that our bounds should be x bounds. Well, that's easy to spot. We actually know what our x bounds are. So pi over 4 is the upper bound, and negative pi over 4 is the lower bound. And our height is our last piece. What's our height? Well, top minus bottom. Now, we didn't label the curves. We probably should have. So we'll do it right now. So the cosine of x is this curve, and the sine of x is that curve. And we look at it and ask ourselves, which curve's on the top? Well, for here, we see it's the cosine curve that's on the top. So for the height, top minus bottom, we are going to get cosine minus sine. So this is not such a bad integral. It's Actually, one we can do. No problems. Cosine x minus sine of x. Well, integrate that. What do we have? Integral of cosine is sine. Integral of sine is negative cosine. Of course, because we already have a negative there, it becomes a plus cosine. Evaluate from negative pi over 4 to pi over 4. All right. Well, we plug it in. Now, sine of pi over 4. Do we know it? We do. Sine of pi over 4 is square root of 2 over 2. Cosine pi over 4, square root of 2 over 2. So, what happens is we get square root of 2 when you plug in pi over 4. If you plug in minus pi over 4, well, sine is an odd function, so you'll end up with minus root 2 over 2. Cosine is an even function. You still have positive root 2 over 2, which means they cancel. So we get root 2 plus 0. I really should have said root 2 minus 0, but the moral is root 2. So there's our mass. So that's our denominator. Good. Halfway. Because we need to take a moment and finish up the other part. So, how do we do moments? Well, it's a little bit more interesting. So, to do a moment, what we need to do is to say, okay, we have to include location. So, if we're doing the moment with respect to the x-axis, it's integral, which means we're adding up start to finish, location, or if you like distance, whichever way makes you remember it, density, height, and width. Okay, so there's our generic formula. A lot of our setup is the same. So we still have negative pi over 4 to positive pi over 4. That's great. Our density is still 1. Our height is still cosine minus sine. Our width is still dx. The only new piece that's being added in is location. Now, what should the location be? Well, the very simple way to say it is when I'm talking about the distance to x, or location relative to x, is we say this should be y. Now, of course, we can't put it as y because we need to have everything in terms of x. So what does y mean? Well, you go here and you say, in terms of the little strip, the y is the halfway point. So that's half of what you would get if you add the two together, or if you like, it's the average of the top and the bottom. So what does this integral become? This becomes, when you clean it up, minus pi over 4 to positive pi over 4. Then you have the 1/2, so we'll just write that 1/2. Cosine plus sine times cosine minus sine becomes cosine squared minus sine squared, and then dx. All right, so that's what we have to integrate. But can we? Well, we could if we could find a way to integrate cosine squared, or if we could find a way to do integral of sine squared. And we start thinking, cosine squared minus sine squared sounds familiar. Sounds like something we should know. And spoiler alert, it is something we should know. So cosine squared minus sine squared, it's one of our nice identities. Do you remember what it is? If not, it's a good time to learn it. It's cosine of 2x. It's the double angle formula for cosine. So we say, hey, that makes the integral all of a sudden a lot easier. So it's minus pi over 4 to positive pi over 4, 1/2 cosine 2x. Well, all right, that we can integrate. Integral cosine is sine. So it's sine of 2x. And now we think what goes in front. Currently we had a half. When we integrate, we have to account for the 2 on the inside, that 2x. So do we divide by 2 or multiply by 2? And why is it to divide? It's to divide, that's right. And the reason is because when you integrate, you have to somehow sort of compensate if you were to run backwards. See, if you were to take the derivative of sine 2x, you'd have cosine 2x times 2. So you're compensating for that multiple of 2 by taking derivative by dividing by 2 when you take an antiderivative. So since we already had a half there, that would get us to a fourth. Then we're going to evaluate from negative pi over 4 to positive pi over 4. Well, that's not so bad. What happens? Well, so you have a fourth. Now, 2 times pi over 4 is pi over 2. And sine of pi over 2 is 1. Subtract sine of 2 times negative pi 4, so that's sine of negative pi over 2. Sine of negative pi over 2, or sine of 90 degrees that's negative, is negative 1. So we get 1 minus minus 1. Okay, so that's really 2/4, also known as 1/2. Okay, so that's our moment with respect to the x-axis. So that goes in our numerator, 1/2. And now we're done, but let's go ahead and make it look nice. What are some things we can do to make it look nice? Well, we can say this is the same as 1 over 2 root 2. If you don't like that, you can say, well, if you multiply by root 2 over root 2, you would get 1/4 times square root of 2. And now we're done, but we should always stop and ask ourselves the question, is our answer reasonable? Because if it's not, we've made a mistake. Well, root 2 is like 1.4 something. Now, if you divide that by 4, 1.4 something divided by 4 is like about 0.3 something. Okay, so it'd be roughly somewhere saying it's along here. That seems pretty reasonable, because if you look at your mass, yeah, you got a good part of it up here, and you got a good chunk down here. It's certainly somewhere roughly in the middle. It's not exactly the middle, but it's roughly in the middle. So this is a reasonable answer. Actually, it's probably the right answer. We were careful, and worked out kind of beautiful in the end. It's kind of amazing, because whenever you have trig involved, you're like, ooh, I wonder if there's going to be a pi in the answer. And this time it's like, no pi, just something simple, something beautiful. What a great way to start. Okay, well, on to another problem. So let's do our next one. Given that a rod has the shape where, well, it's 0 less than equal to x less than equal to 1. Of course, the shape of a rod is just like this. It looks a lot like a pen, for instance. Okay, the density is what? 2 plus 2x over 1 plus x squared. Determine the center of mass of the rod. All right, well, let's think about it. Now, this is a one-dimensional thing. So how do we find the center of mass? Well, for the center of mass, we usually write it as x bar. By the way, this notation, whenever you see a little bar on top of something, it's usually referring to some sort of an average. So that's what we mean when we see that x bar. That's the x coordinate for the center of mass. And everything's in terms of x, it's just one-dimensional. So it is the moment with respect to the origin, or if you like, with respect to 0, over the mass. So we have to compute two different things. What's the mass, and what's the moment with respect to 0? Well, mass, that's pretty straightforward. Mass says you're adding up, start to finish, of your density times your distance. And that's your mass. Okay, well, no big surprises. So we know where we start and we finish, 0 and 1. We know our density right there, 2 plus 2x over 1 plus x squared. And our distance, because it's a rod, it's dx. All right, good. Well, now we have our setup. How do we proceed? Well, in this case, it's not so bad, because we can do something called algebra. That says, hey, think of it in the following way. Break up that addition in the numerator. You see, we're allowed to break up addition in the numerator. Not the denominator, but the numerator. So we can write this as 2 times 1 over 1 plus x squared plus 2x over 1 plus x squared. So there we go. Now what happened? Well, we thought of it as like, hey, there's this 2 over 1 plus x squared and a 2x over 1 plus x squared. And I'm just taking this 2 on the first term and putting it to the side. Now, why do that? Well, in some sense, I see 1 over 1 plus x squared. My heart starts to flutter a little bit. That's something beautiful. That's arctangent, and I like that. Now, 2x over 1 plus x squared, that's not so bad either. Because if you think about what's happening, it's a situation where if you compare the top and the bottom, they have a nice relationship. And in particular, if you think of the bottom as being a u term, then the 2x would be a du term. So it's a case where I have a function downstairs and the derivative upstairs. Whenever I see that, I say, hey, that means it's like a log. Because that's how, when you take derivative of log, you have the function downstairs, the derivative upstairs. So now I'm like, it's an arctangent, and there's a log. I see how to finish everything. Woohoo! Cool! So, this is great news for us. We have 2 arctangent of x plus log of 1 plus x squared. And then we're going to go 0 up to 1. Now, if you plug in 0, log of 1 plus 0, log of 1, 0. Arctangent of 0 is 0. Good. Plug in 0, you get 0. Plug in 1. Arctangent of 1. Oh, we should know that one. Arctangent of 1 is pi fourths. Because tangent of pi fourths, so if you think about that 45-degree angle, then what you see is the opposite over adjacent are equal. So tangent of 45 degrees is 1, which means tangent of pi fourths is 1. That's why arctangent 1 is pi fourths. Okay, we knew that, right? Of course we did. So 2 times that would give us pi halves. Plus 1 plus 1 squared is 2, so log 2. That's our mass. So that is what goes in to our denominator, pi over 2 plus log 2. Okay, are we done? No, we need to take a moment and finish up the problem because we also need our moment. We need our numerator. So how do we do that? Well, the moment, that works in a very similar way. The only thing that we need to do is add one more piece. So our moment is going to have adding up a to b, location, density, and distance. Where location is the only part that really changes. And so as long as we understand what that is, then the rest of it's very simple to adapt because it's good to be adaptable. So the location is x. That's what we mean. So what ends up happening is it's essentially the same integral we had before, but now there's an extra factor of x upstairs. So we have 2x plus 2x squared over 1 plus x squared. So that's what we have to integrate. Now we say, hey, that first piece, we're good to go. We know how to handle that. It's that 2x squared. That is going to require some thought. But here's an idea. We say, what's good? Well, there's a way to think about what's happening here. Is I want to get rid of that 2x squared. And I say, it kind of looks like x squared. It does. In fact, 2x squared is twice what x squared is. It's a true story, true story. So I say, well, 2x squared is almost twice of what I have downstairs. Almost. The problem is, to have the twice downstairs, I need to have a plus 2. So, add 2. And then I probably, you can't just add 2. That's crazy talk. Then we say, well, wait, what if you also subtract 2 right away? See, adding 2 and subtracting 2 is like adding 0, which means you don't do anything. That's the beautiful thing about adding 0. So we're going to do an add to and subtract to right on the very end. So if you were to do that, what would happen? Well, it would really say you have the following. You'd have 2x over 1 plus x squared. Then your next two terms would be 2x squared plus 1 over 1 plus x squared. And then your last term would be a 2 over 1 plus x squared. All right? So you can convince yourself, right? The plus 2 and the minus 2 would cancel out, and so everything works as you would think. Now, in this setting, we see that certain pieces are pretty easy because they're just like what we did before. For instance, this first term, that's the natural log of 1 plus x squared. The last term, it's like what we had here. It's the minus 2 arctangent of x. Then there's this middle term. How do we handle that? Well, here we look and say, look, x squared plus 1 and 1 plus x squared cancel each other out. So what it really is simply just the number 2. And that's easy to integrate. So this would be plus 2x. And now life is good. When you plug in 0, again, log of 1 is 0, x is 0, arctangent of 0 is 0, all goes away. Plug in 1, you get log of 2 plus 2 minus 2 times arctangent of 1, which is pi halves. So that's what goes here. Log of 2 plus 2 minus pi halves. Well, okay, let's clean it up. And the reason I say clean up, you have a fraction. Pi over 2 is inside a fraction. Okay, I don't like fractions within fractions. It's not wrong. I just don't like it. So I'm going to do something called multiply the top and bottom by 2 just to get rid of my fractions and fractions. And doing that leads us to natural log of, well, I'll write as 2 log 2 plus 4 minus pi divided by 2 log 2 plus pi. And there you go. Now, one thing you could do if you wanted to be really mysterious and obfuscate what just happened is you could say, hey, 2 log 2 is the same as log 4. And so if you put in a log 4, people are like, whoa, where did that log 4 come from? How mysterious of you. But of course, no, it's really just the same. Well, is it reasonable? It's not so obvious, but you should think to yourself, okay, what's bigger, the top or the bottom? First off, is everything positive? Well, log of 2 is positive. 4 minus pi is positive. So yeah, everything's positive. So you end up with a number that's strictly greater than 0, which is good. On the other hand, 4 minus pi is certainly smaller than pi, which means that the numerator is smaller than the denominator, which means we're between 0 and 1. That's a good sign. Our center of mass should be somewhere between 0 and 1 because that's where our rod is at. So a reasonable answer. Maybe not the easiest number to figure out, but at least a reasonable answer. So a good sign, a good sign. All right. On to another problem. Here we go. You have a special machine which can form a straight rod where the density at a given x is A plus BX kilograms per meter, where A and B can be set as needed. So, in other words, we can adjust our density to satisfy customer demand. Who knows? They may say, look, we want to have uniform density, or maybe we want to have one end be really thick compared to the other end. Uniform density would be B equals 0. If B is large, then as you move from one end to the other, it gets a lot thicker. Okay, so given that you want the rod to be 2 meters, okay, all right, so that long. Have a mass of 2 kilograms, so we know our mass is set. And the center of mass needs to be at 5/4 meters. Then determine how A and B should be set. Well, okay, so we can kind of start visualizing what should be true. Well, we have a rod we know we're going from 0 to 2. Notice where our center is. See, if I go from 0 to 2, halfway would be 1. So we're biased towards 2, because 5/4 is 1.25. So pictorially, it's like, well, it should sort of get a little bit thicker towards the 2. So that when we look here, our center of mass should balance at 5/4. So one thing that should be clear is at the end, B should be positive so that we get that sort of increasing thickness to help us bias towards the right-hand side. We should also hope that A should be positive, because if A is negative, then we somehow have negative density. That doesn't make sense. Density should be a positive quantity. Okay, well, let's get into it. So let's start with what we can say for sure. We know something about the mass. So the mass is 2. So 2 is our mass. And we know how to find mass. It's the integral, start to finish, 0 up to 2. And then what do? Well, it's going to be our density times our length. So density times length. Okay, so no big surprises. So what do? Well, we integrate that. And I'm just going to make a note so that when I come back to look at this later, I can make sure I understand what's going on. It's nice to sort of document what you're doing so that when you look at something later, you say, aha, I can follow my arguments. You'd be surprised how many times you're doing something and then you go back to look at it, 5-10 minutes later, you're like, what was I doing? What was I thinking? Well, if you write notes and you're like, okay, this represents this represents that, you're like, oh yeah, that's exactly what I was thinking. Another thing that helps, this is a little side note, write legibly and in a nice organized fashion. It's amazing how hard it is to be like, you see these little pieces and you're jumping all over the place. Whereas if you just it's so much easier to follow. Okay, sorry. Back to our regularly scheduled problem. So here we go. We're going to get ax plus 1/2 bx squared. All right. And then evaluate from 0 to 2. Well, plug in 0, you get 0. Plug in 2, we get 2 times a, okay, and then 1/2 times b times 4. So that's 2 times b. Okay, so we have that 2 is 2 times a plus 2 times b. Aha! That tells us that a and b are connected by an equation. Nice. Cool. So another way to say this is that a plus b better be equal to 1. Now, that's the mass. Let's get into our center. Well, let's, we should probably take a moment, right? Yeah, exactly. We need the moment. So let's think about the moment. So our moment says what? Well, m0 divided by, well, we'll go ahead and say it this way. 5/4 is equal to m0 divided by m. But we know what our mass is. We know it's 2. So we could say that 5/2, that's our moment with respect to the origin. All right, so now we know what our moment is, and that is integral 0 to 2. And then we have to have our location, x, and density, a plus bx, and length. So again, I'm just going to make a note here. X is location. There we go. Good. All right. Well, this is integral 0 to 2, a times x plus bx squared. All right. Well, that's something we know how to integrate. That would be 1/2 ax squared plus 1/3 bx cubed. And now we need to evaluate from 0 to 2. Nice thing is when you plug in 0, you get 0. If you plug in 2, 2 squared is 4 times 1/2 gives us 2a. 2 cubed is 8 times a third is 8 thirds. So 5 over 4 is equal to 2 times a plus 8 thirds times b. Well, let's get rid of fractions. How can we get rid of fractions? Multiply everything by, 5 over 2, not 5 over 4. 5 over 2 is equal to 2a plus 8 thirds times b. Multiply by 6. If you multiply by 6, then all our fractions go away. So here, 5 over 2 times 6 would tell us 15 equals, here, times by 6, 12a. And here, 16b. So now we have another relationship. So, two equations. A plus b equals 1, and 12a plus 16b equals 15. So two equations, two unknowns. Well, let's think about it. That's kind of, I like to say, our bread and butter. We know how to solve these. We do it by combining. So, for instance, suppose we started with 12a plus 16b equals 15, and then underneath we put a plus b equals 1. Well, what can we do? What can we multiply by to say, well, let's say we want to get rid of the a so that we could solve for b. Well, to do that, we would say, well, let's multiply by negative 12. If we do that, 12a minus 12a would be 0. 16b minus 12b is 4b. And 15 minus 12 is 3. So that leads us to the conclusion that b should be 3/4. Okay? Well, how about a? Well, now, look, I can substitute in. So that tells us that a plus 3/4 has to equal 1, or a should be 1/4. Good. So remember, we said, look, a should be positive in order to make sense. Otherwise, it could be a badly written problem. But not our calc teachers. No way would our calc teachers write a bad problem. I don't believe that. But the other thing is that's good is we said, hey, our intuition says b should be positive because it should be getting thicker as you go towards 2. And that's definitely happened, that b is 3/4. So what are a and b? Oh, they are, and we'll just put them together, a equals 1/4, b equals 3/4. And there we go. We're done. Nice. Good. Good. Fun problem. Interesting. Different, It's like, okay, what do? You have A, you have B. How do you put everything together? So let's go to our next problem. Let R be the circle of radius 2, centered at the origin. Given that R has density, absolute value of x cubed, then determine the mass of R. Okay, let's think of the picture and think about what we should do. Well, it's a circle centered at the origin. Okay, so we draw our axes. Radius of 2. So, for instance, here is positive 2. Here's negative 2. And it's not a uniform in the sense that we have uniform density. So it's going to be thicker in some parts and thinner in other parts. So notice how our density is set up. Our density is the absolute value of x cubed, which means that when x is small, it's very non-dense. But as x gets larger, the density goes up. So if we were to sort of shade this by density, we would say it's very dense for our larger values of x, so over near the ends, but very sparse in the center. So something maybe like that, right? Okay, kind of, roughly speaking, that's what would happen. Okay, so dense at the ends, sparse in the center. Why do we have absolute value? Well, we can't have negative density. Density should be positive. So it's sort of like you can't have antimatter. Like everything has a positive measurement. So that's why there's absolute value. Well, this is two-dimensional. We can see that because density is a function of x, we need to slice in a way where we are taking our thin vertical strip. So we're going to integrate with respect to x. So let's think about our setup. We're going to have adding up our pieces. So we have our mass. We're adding up, that's integrating start to finish. And then we have our density. And we have our area. And our area is a combination of height and width. All right. So some of these pieces are pretty easy to spot. So the density, oh, that's given to us. That's the absolute value of x cubed. Our width, that's our dx. Now, let's talk about our height. Our circle of radius 2, the way we would start is saying, well, that's given by the formula x squared plus y squared equals r squared. Well, that's x squared plus y squared equals 4. So if you solve for y, you'd subtract x squared and take the square root. So you get y equals the square root of 4 minus x squared. Now that's the top half. The bottom half would be y equals minus the square root of 4 minus x squared. So the total height is twice that. So it's 2 square root 4 minus x squared. All right, so that's the height. And what are our bounds? Well, they're from -2 to +2. Okay, so that's our setup. Let's start doing things to help clean it up. So what's something we can do? Well, one thing we can do is say, you know, there's an absolute value there, which is going to make things messy. Let's remove the absolute value. How could we do that? How could we take our absolute value out of the problem? Well, the way we can do it is we can say, let's use symmetry. You look at the picture, you see it's the same on both sides, right and left. Or at least it would be if I was a better artist. But you're a better artist, hopefully. You can say, oh, yeah. So if I turn it over, it's the exact same. Which means I only have to do half of the picture and then double, and now I see the whole symmetry. I see the whole mass. So instead of going from -2 to +2, we just need to go from 0 to 2. So we're going to do the following. We're going to go from 0 up to 2. But if we do that, we have to double our result. So we're going to have a factor of 2. Notice we already have a factor of 2. 2 times 2 gives us 4. So this 4 comes from the 2 and by symmetry. Now we can drop the absolute value. So we have x cubed and square root of 4 minus x squared. Well, you can write it as 4 minus x squared to the 1/2. Okay, good. Good. That's what we need to integrate now. Well, how do we integrate this? Well, it's not one of our basic integrals, so we have to do something to integrate it. And we start thinking, well, there's not really a nice algebra thing because square root does not work so cleanly over square root of something minus something. And we might say, well, it sounds like a very high power technique is needed, but let's not try to pull out a big tool when a small tool works. When we don't have any algebra, when there's no trig, when it's not one of our basic functions, the other thing we look for is a substitution. And when we're thinking of substitution, one of the things that we often look for is ask the question, what's on the inside? Well, in this case, there's really one place to look for the inside, that to the 1/2 power. And the reason I say look on the inside is that substitution is an inside job. So we're going to think of this 4 minus x squared. We'll say, look, here's the inside. Let's suppose, hypothetically, let's explore, what if we made u equal 4 minus x squared? We could do that. Well, what would happen? Well, du would be minus 2x dx. And now at this point, there's one of two reactions. Like, well, this is never going to work. Or, ha, I see how it's going to work. The correct response is the second one. Aha, I see how this is going to work. Now, you might say, well, wait, hold on. What about the -2? Easy to fix. It's called move it to the other side. So I'm going to take the -2 over here. It's a -1/2. Now you're probably thinking, but Steve, I'm going to catch you. That's an x. You have x cubed. To which I say, but x cubed is x squared times x. And you're like, ooh, you're right. It is x squared times x. But how does that help us? One x we pull off and say x dx, I can replace it in terms of du. The other x squared, notice, we can replace an x squared by 4 minus u. So, what do we have? We have the following. Let's put it all together. If we carry out this substitution, we have that 4. We're going to get in x dx is a -1/2 du. So I'm going to pull out the -1/2. And then we have the integral. Then we have a du. So the x has already been accounted for because that x dx became part of the du. So just keeping track. There's an x squared. Well, that's 4 minus u. There's a 4 minus x squared to the 1/2. That's u to the 1/2. And now we update the bounds. So don't forget the bounds. Well, plug in 0. 4 minus 0 squared is 4. Plug in 2. 4 minus 2 squared is 0. Now, we don't like going from a high number to a low number. Well, let's swap. If we swap, we got to change the sign. Well, hey, that takes care of that sign. You see, we're like, well, a negative. We can't end up with a negative mass. We're like, oh yeah, switching. Oh, cool. And the negative works out. So what do we have? Well, 4 times 1/2 would give us 2. And remember, the negative goes away because we're switching the bounds, 0 to 4. And now we can do our fun algebra thing called distribute. So this becomes 4u to the 1/2 minus u to the 3/2 du. And now we're like, hey, this is a reasonable integral because this is a reasonable integral. So we have the 2 out in front. Then we have 4. It'll be u to the 3/2. You add 1 and multiply by 2/5. And then, 2/3. I'm getting ahead of myself. This will be the 2/5. Minus, here you add 1, 5/2, multiply by 2/5. And from 0 up to 4. Now, the good news is when you plug in 0, you get 0. 0 to 3/2, 0 to 5/2, that's 0. So we only need to plug in 4, clean it up, and we'll be done. So, what do we have? Well, we have the 2 out in front. Then we have 4 times 2/3, which is 8/3. And then we have 4 to the 3/2. Now, we could do 4 cubed is 64, and the square root of 64 is 8. Or you could do the square root of 4 is 2, and 2 cubed is 8. So either way, you end up with an 8. Minus 2/5 times 4 to the 5/2. Now, we say, well, 4 to the 5th, that's 1,024, and the square root of 1,024 is 32. Of course, the easier way to do it is say the square root of 4 is 2, and then 2 to the 5th, well, that's 2, 4, 8, 16, 32. So that's 32/5. And now if you look, it's like, 8 times 8 is 64. 2 times 32 is 64. So you can pull out a 64. And there's already a 2 in front, so that gets you to 128 times 1/3 minus 1/5. 1/3 is 5 over 15. 1/5 is 3 over 15. So that would give us a 2 over 15 times the 128, which would leave us with 256 over 15. And there we go. We're done. We're done. And it worked out. One of the amazing things, this problem involved circle, right? The circle radius too. And oftentimes whenever we see a circle, we're like, hey, there might be some pi in this problem. But this problem, no pi. That's okay. Doesn't have to have pi in the answer. It might not. And this time, it didn't. Well, such is life. All right. Well, we move on. Keep going. Because we have more problems to do. Our next problem. Find the value of a, so the region where we have 0 less than or equal to y less than or equal to x, and 0 less than or equal to x less than or equal to 1, and density is x to the a, has y bar is 2/5. Okay, so let's sketch our region. Well, it's actually not so bad, right? Because we know that y goes from 0 up to x. So y equals 0 is the axis, and y equals x is, well, it's y equals x. So it's a triangle, and it's this triangle right here. So here we go. Here's our triangle. So there's our region that we're after. And what happens is we have our density. Density is x to the a. Now, of course, depending upon what a is, it influences where does the density go. Do you have more density towards 1, or do you have more density towards 0? Is it somewhat uniform in terms of density? It's not so clear because, well, we got to figure it out. But one thing is for sure clear is because we see it's a function of x, that says we're going to have to slice in this way. Okay. So we're going to sit down and start thinking. We're after y bar is 2/5. So we have that 2/5 is y bar, which is, well, we got to do our integrals. Let's do some integrals here. So our mass is adding up, start to finish, and we'll have our location. Well, sorry, mass doesn't have location. It's our density. I was thinking of the moment. I was having a moment there where I forgot. So it's density times area, and area is height times thickness. All right, so what does that translate to for us? We're going from 0 to 1. Our density, x to the a. Our height, we're going from 0 up to x, so that's x. Our thickness is dx. So this is the integral 0 to 1 of x to the a plus 1. All right, so far so good. And, well, that's an easy integral. You add 1 to the exponent, a plus 2, and divide 1 over a plus 2. And evaluate from 0 to 1. Now you plug in 0, you get 0. Plug in 1. 1 to the power a plus 2 is 1. Well, 1 to any power is 1. Sounds so obvious when you say it. We've had students get tripped up before, like, what is 1 to the a plus 2? I don't know. I don't know. Ah! Now we know. And knowing is half the battle. Okay, so this simply becomes 1 over a plus 2. So, in terms of y bar is mass, our moment over our mass. So we've computed our denominator. So it's something 1 over a plus 2. Now we've got to do the moment. So the good news is the moment is almost identical. So we won't write it fully out. What's the only difference? So when we're doing the moment, there's one extra piece of information that we have to take into account. That one piece of information is location. So for the moment, it's going to be the same integral, 0 to 1, but we add one piece, x. So that's our moment. Whoops. I forgot to write this down. What is y bar? Y bar, I put m0. It's mx. And now I have to go back and check this. Okay, so it's the distance to the y-axis. It's not x. I put a mistake there. Let's fix it. See, this is why you have to check your work. It is x over 2. Okay, so we should make sure we're not making too many mistakes, right? So where is this x over 2 coming from? The way you should really think about it is you should say, you take your slice, where's the center? It's halfway. And now, where is it in relationship to the x-axis? Because we're taking a moment with respect to x. So it's half x. So if this is 0, this is x, this is half x, so our distance down is half x. If we were doing m sub y, so distance to the y-axis, that length is just x. Okay, all right, we should slow down so we don't make mistakes. So location, x over 2. Height, still x to the a. Density, still x to the a. Height is still x. Thickness is dx. So we end up with 1/2 integral 0 to 1 x to the power a plus 2. So that's essentially, we have a half, and we increased our exponent by 1. So not too big of a change. So 1/2, 1 over a plus 3, x to the power a plus 3, evaluate from 0 to 1, and if you plug in 0, you get 0, you plug in 1, this term becomes 1, so you end up with 1/2 times 1 over a plus 3. And that's what goes upstairs. So we have 1 over, and I'll write it as 2 times a plus 3. Okay, so that was the hard part. Now, the rest of it is just finding an answer, because we have one equation, one unknown. Perfect. If you think about taking that 1 over a plus 2 that's downstairs and moving it upstairs, you'd flip it over. So this would give you a plus 2. Downstairs it would be 2a plus 6, because I can multiply the 2a plus 3 times 2. Cross multiply. So you'd have 4a plus 12, right? 2a plus 6 times 2 equals 5a plus 10, right? 5 times a plus 2. Move terms around. So you move terms around, subtract 4a, subtract 10, and we come to the conclusion that a is 2. And so it worked out kind of nicely. Probably the numbers were chosen so that it would work out nicely. So be careful. You can see here I was kind of tripping myself up along the way. It's easy to lose track of things. So make sure you have the right kind of moment. Make sure you're using the right kind of measurement. These things matter. We don't want to make small mistakes and end up costing ourselves, important points. But okay, we're patient. But now on to our next problem. So on to our next one. Woohoo! Ooh, it looks kind of similar. Hopefully this time we'll make fewer mistakes. Find the value of a, so the region where we go from 0 up to x to the a, with 0 less than or equal to x less than or equal to 1, and constant density has x bar equals 4/5. So it's a little bit different than the one we just did. So if you think about what was happening, in the other one we were saying, hey, our density is going to change. This one we say, no, density is constant. What's going to happen is our shape is going to change. So it's like, pick just the right shape. Because you can imagine, it just depends what a is. You could have something where you might have, x to the a. If a is very small, like a square root, it might look like this. If you have a is 1, yeah, it might look like that. If you have a is larger, it might look like this. So it's sort of like, we got to pick out which one of these is the right one. Well, what do we want? We want to have our x coordinate be a little bit towards the right-hand side, because we're going from 0 to 1. We want it to be at 4/5. So we want it to, so if here's 1, we're kind of hoping to get over towards the end. And so we think to ourselves, well, what will do it? I'm thinking it probably might be more like this is my guess. I don't know. We have to figure it out. But let's just, for now, let's think about maybe that's the right picture. And who knows? Who knows? So we're picking the right shape. Now we see the words constant density. And if you ever see something that says constant density, you should say to yourself, hey, that's just shorthand for saying constant density means density 1. Now, it might not truly be 1, but when it comes to center of mass, you might as well assume that it's 1 because it doesn't make a difference. That's the nice thing about constant density. So let's get into it. We have x bar. Well, that's our moment with respect to the y-axis divided by our mass. So our mass, we are going to add up, start to finish. We have our density, our height, and our thickness. So that's just our generic formula. So for us, we say, okay, we're going 0 to 1, start to finish. Our density is 1. That's easy enough. Our height is x to the a, because that's what we're told. And our thickness is dx. So, oh, this is great. We can integrate that. That would be add 1, so you get x to the a plus 1, then 1 over a plus 1, and there you go. Okay, evaluate from 0 to 1, and that becomes 1 over a plus 1. So that's our denominator. So 1 over a plus 1. Good. Now, what about our moment? Well, let's start working on that. So what do we have? We have that our moment with respect to y, so m sub y, is adding up a to b, and then we have our location, our density, our height, and our thickness. Okay. Well, so since we're going to m sub y, well, if we think about our slice, m sub y is our distance to the y-axis. So m sub y is simply going to be x. Our density is still 1, our height is still x to the a, and our thickness is still dx. So this becomes the integral from 0 to 1 of x to the a plus 2. And, all right, sorry, x to the a plus 1. Got ahead of myself because I'm seeing the next step, right? We're integrating that. So when we integrate that, that's 1 over a plus 2, x to the power a plus 2 from 0 to 1, and that would be 1 over a plus 2. Okay, so that's our numerator. All right, 1 over a plus 2. Well, okay, if we clean that up, we can certainly take that 1 over a plus 1 downstairs, flip it up, and doing so says, hey, our x bar is a plus 1 over a plus 2. All right, and what do we want? Well, we want x bar to be 4 over 5. And now we say, well, that's great. We can handle that. We can cross multiply. And so if we do our cross multiplication, 5a plus 5, so 5a plus 5 is equal to 4a plus 8, right? And then we move terms around, and we come to the conclusion a is 3. And that's it. We're done. And it matches with what we think should be true, right? We said it kind of should look more like that. And that is what an x cubed would look like. So there certainly is a lot more shape towards the one part, because it's very short over there in comparison. Good. Nice. Good times, good times. All right. Well, let's try another problem. So, find y bar for the region where x goes from 0 to 1 and y goes from 0 to this crazy root 1 minus x to the fourth. Okay, so this is the picture. They actually gave it to us. And our density is 2x. All right, well, let's think about it. We can mark some things here. So this is 1. It's also pretty easy to see that that's 1 as well. Looking at this problem, the fact that density is a function of x says that when we think about how to integrate, definitely we need to do our slices in this way. So, how do we begin? Well, what do we need? We need to find y bar. We know how to find y bar. It's given in the following way. Y bar is equal to our moment with respect to x divided by our mass. So really this is saying we need to compute two things, our moment and our mass. Well, let's get into it. How do we do it? Well, for here, we think and say, all right, let's start with mass. Mass should be the easy one, right? So how do we do mass? Mass is adding up A to B. Integration is all about adding up. And then you have your density times your area. Well, area is height times width, because we're thinking of our area as the area of a little slice. So height times width. So for us, well, that's saying 0 to 1, the density, which is 2x, the height, well, the height is from the bottom curve to the top curve. Well, the top curve is the square root 1 minus x to the fourth. And the bottom curve is 0, so that's our height, dx. Okay, so now all we have to do, it might take us a little bit here, is to integrate that. So, okay, we can't do some simple algebra. The square root doesn't mix well with this, subtraction going on in the middle. So there's not much algebra here. This is not one of our automatic integrals. So we start thinking about substitution. Now, if we think substitution, of course, a natural first guess is to say, hey, substitution, it's an inside job. Look at the function on the inside. Well, the inside function is 1 minus x to the fourth. Okay, if u equals 1 minus x to the fourth, well, then we get du would be minus 4x cubed. The minus 4 is okay. I'm not excited about the x cubed. The problem is I only have an x. I can't really get an x cubed there. It's just, okay, all right, we got to give up on this one because there's not really a way to recover. See, in a previous problem we had, there was this extra, there was extra x's. And so we were like, hey, let's recover by just taking care of the extra x's. Here, there's an x deficit. And it's really hard to overcome deficits. Excesses were fine. It's when we have deficits that we have problems. So maybe that's the wrong substitution. Okay, so let's cross that substitution out and think about a different option. Well, the other place to look when you're thinking about substitutions is to say, well, do I have a derivative of something nice? I see 2x here. There's a derivative that often involves 2x in the answer, and that is if I ever take the derivative of x squared. So this is suggesting something to us. This suggests, hey, since we see a 2x dx, maybe we should set u equal x squared. Then we get a nice derivative, 2x dx. Of course, if we set u equal x squared, we have to say, but does that make sense in terms of the problem we have? Well, we got to look. We have to really look into this part and say, well, can we do anything with x to the fourth in terms of x squared? Well, x squared squared is x to the fourth. Okay. All right, so we can make progress. So this would become adding up. We've got to figure out the bounds in a second. The 2x dx becomes our du. And since x to the fourth is x squared squared, this becomes square root of 1 minus u squared. Now we have to think about our bounds. You see, we have currently 0 to 1. Now these are x bounds. X equals 0 to x equals 1. So when we are talking about our bounds right now, our bounds from 0 to 1 are only in terms of x, not in terms of u. We've got to take our x bounds and make them u bounds. See, the 0 to 1, those are x bounds. They're not u bounds. We got to switch to u bounds. So we are not going to be going from 0 to 1. Instead, we're going to be going from 0 to 1. Okay, good. Right. Now you're probably like, what? They're the same. No. There's a subtle difference here. What's the subtle difference? Well, it's what we said. See, when we talked about 0 and 1 here, it's x equals 0, x equals 1. When we talk about 0, 1 here, it's u equals 0, u equals 1. So that's what we mean when we say they're not the same, that there's this transition. What do they correspond to? But we still have a challenge. How do we integrate this expression? It certainly is easier than what we started with. It doesn't mean it's easy, just easier. And then we look at it and say, hold on. We've seen this before. Do you remember where we've seen this? It's part of a circle. You see, we can look at this and say, aha, we can interpret. And in particular, the way we interpret is we say, this is a 1/4 of a unit circle. And in particular, when we say it's 1/4, it's the area of 1/4 of a unit circle. So the original expression, this is not a circle. You can kind of see it's not very circle-like. It's kind of like a little bit flatter on the top and a little bit steeper descent down. But after the substitution, we say, oh, it becomes like a circle. And therefore, we say, hey, that means that this is pi fourths. 1/4, that's where the over 4 comes from, of a circle of radius 1. And a circle of radius 1 has an area of pi. So that is our mass. So that's the downstairs. Well, that should make the upstairs really interesting. I wonder what is going to happen there. Well, let's find out. Okay, so now we have to do our moment. So our moment with respect to x. We're going to add up, and the thing that changes is there's now a location. But everything else is still the same. So location, density, height, and width all come together. So the last part, that's the same. Let's talk about our location. What is our location? Well, if we're thinking about it, we're looking for our location relative to the x-axis. So if I'm looking for location relative to the x-axis, we say, okay, that would be, if this is my center, that's this distance right there. So our location is going to be 1/2 of square root 1 minus x to the fourth. It's halfway down. So here's square root 1 minus x to the fourth. It's halfway there. Our height also is the same as before, square root 1 minus x to the fourth. We'll put our density in here because we can. It's 2x. Here we have dx. And you'll notice lots of beautiful things happen. Our bounds are 0 to 1. Same bounds as before. The half and the 2 cancel. But it gets better. So there's an x. What else happens? The square root of 1 minus x to the fourth, the square root of 1 minus x to the fourth. Well, that just becomes 1 minus x to the fourth. There's no more square root. And now it's a beautiful integral. No tricks. No like, interpret it this way. Here's a substitution that's kind of hidden. No. There it is. All out there in the open, ready for us to pluck it and get the answer. So we first multiply. So this is really x minus x to the fifth. And now we say, well, that's a half x squared minus a 6, x to the 6. Got to evaluate from 0 to 1. So we end up with a half minus a 6. It's easy to plug in 1, even easier to plug in 0. Now, 1/2 is the same as 3/6. So 3 over 6 minus 1 over 6 leaves us with 2 over 6, also known as 1/3. So our moment is 1/3. So when we put this all together, what ends up happening is the following. You can take that 4 downstairs and flip it over. And so we end up with, this is 4 over 3 pi. And there you go. There you go. Now, of course, you want to say, is it reasonable? Well, let's think about it. 4 over 3 pi. Well, 3 pi, 3 times pi is definitely over 9. So 4 over 9 would put it a little bit below a half. So it's saying that the y-coordinate should be somewhere a little bit underneath a half. And as we look at the picture, we're like, that makes sense. Because if you think about it, there's no part of the curve other than here, it's at 1. So the y-coordinate should be a little bit below a half. Because, we're definitely missing pieces there. So, okay, yeah, that's a reasonable answer. And we would definitely start being like, if we saw a negative answer, we're like, whoa, that can't possibly be right. But we didn't see a negative answer. We saw something that looks pretty reasonable. So there we go. There we go. Good. Good. Well, on to another problem. Here we go. Find the center of mass for the constant density region where x goes from 0 to pi and y goes 0 to sine x. Okay, so now we have to find not just x bar or y bar. We have to find the whole thing, everything. All right, well, let's save ourselves some work. So, first off, constant density is our favorite type of density. And we can pick our density, so we'll pick density equals 1. Why not? Make it simple. And we look at our shape, and wherever we're asked to find a center of mass for a shape, we look and say, is there any symmetry? Well, here's an obvious symmetry right here at pi over 2. Now, we have to check two things. First off, is the shape symmetric? So in other words, if we took it and turn it over, would it still look the same? The answer is yes, the shape is exactly the same. Is the density symmetric? In other words, if I have a density over here and I track to where it goes, is it the same amount of density? And because it's constant density, that's an easy question to answer. It is symmetric. Life is good. Woohoo! We have a nice shape to work with. Now, what comes next? Well, we stop and say, hey, by symmetry, we should make note here. We have that the x-coordinate is pi halves. So the only thing left is the y-coordinate, which is where we're probably going to spend most of our time. So how do we find the y-coordinate? Well, to find the y-coordinate, we say the y-coordinate is the moment with respect to x divided by the mass. So we have to go through and run these computations. We'll start with the mass. So we'll do it over here. Mass is adding up, start to finish. We have our density, our height, and our width. Okay, that's just our generic formula. It's always nice to start with our generic formula, and we start figuring out what happens. So for us, Well, we see where we're going from. We're going from 0 to pi. That's good. Our density is 1, so we don't even need to write it. Our height, well, we should have been explicit and said we're going to slice this way. Why? Well, because our function here is a function of x. So since we're starting with something which is a function of x, it's good to integrate with respect to x. So we're going to do vertical slices. So 0 to pi, height is sine of x, and the width is dx. Well, that's one of our 10 basic integrals we need to know. Integral of sine is negative cosine. Evaluate from 0 to pi. So that's negative cosine pi minus cosine of 0. Well, cosine of pi is negative 1. So negative of negative 1 is 1. So this is really 1. Minus makes a plus. 1, which is 2. Aha, beautiful. It's 2. Well, of course, in fact, here, when we have constant density of 1, mass is really just area. So we've done that before. We've actually found the area in the sine curve before. So, well, it's been a while, though. So it's not bad to do it again. Okay, so our denominator is 2. Well, we suspected that would probably be the easier part of the computation. Let's turn now to our numerator. So what's our numerator? Well, our moment with respect to x, it's going to be a little bit more because there's an extra piece. Whenever we talk about moment, we're going to have a location involved, or if you like, distance. Either one, think of it. Location is technically a little bit more correct, but as long as you remember how it works, that's the important thing. So location, a density, a height, and a width. So for us, the location, where is it? Well, we're talking with respect to the x-axis because that's the x. So we pick our little slice, and here's our center of our slice. So our location is that distance. Well, what's that distance? It's the halfway point. So our location here, which we're thinking about, this is really y. It's 1/2 sine of x. Because the top part is the sine function, the bottom part is 0, halfway in between is 1/2 sine x. Now the rest of it's still the same. So density is still 1, height is still sine, width is still dx, and our bounds are still the same. So this becomes the integral 0 to pi 1/2 sine squared x. So that's what we need to compute. Well, so how do you integrate sine squared? And the answer is we don't. What we do is look for a way to rewrite sine squared as something easier to work with. So how do we rewrite sine squared as something easier to work with? Well, we reach into our bag of identities. Now, in our bag of identities, there's a nice one that says sine squared is the same as 1 minus cosine 2x over 2. So this is called power reduction because it takes that squared and says, hey, I can rewrite something without a square. So it's reducing the power down. It's a power reduction. Well, you had a half already. There's another half showing up. That's a fourth. I'm going to go ahead and just pull that out. So 1/4 integral 0 to pi of 1 minus cosine 2x. So the half and the 2 become the fourth. Well, now we're ready to integrate. X, integral cosine is positive sine. There's a minus, so minus sine 2x. Don't forget, you also have to account for this 2 on the inside. And the way you do it is you divide by 2 and evaluate from 0 to pi. Well, what will it be? Well, when you plug in pi, you get pi there. So we have a pi, and there's a 1/4, so there's a 1/4 pi. Sine of 2 pi is 0. Goes away. Plug in 0. 0. Sine of 0 is 0. So it simply becomes 1/4 pi. Well, I don't know if simple is the right word, but it does become 1/4 pi. So this becomes pi over 4. Well, now we put those together. Pi over 4 over 2 becomes pi over 8. Well, if pi is around 3, it's a bad estimate, 3/8. It's actually a little bit more than 3/8. But again, 3/8, it's less than a half. So something around here. So it looks like it's saying the center of mass should be roughly a little bit less than half, there, somewhere around there. Okay, that's the reasonable answer. Reasonable answer. Now, what does our answer look like? We need to combine the x and y coordinates together. And so we say our final answer, pi over 2 minus pi over 2 comma pi over 8. Why was I thinking subtraction? X coordinate, y coordinate. There we go. That's it. That's where our center is at. Cool. Beautiful. Lovely problem. Lovely problem. All right. And let's do one more problem. One last problem to help us finish up. Find the center of mass of a thin plate bounded by the parabola x equals y squared minus y and the line x equals y if the plate has uniform density 2. Well, the fact that it has uniform density 2 really could have chosen any number. I suspect it chose 2 just to make the numbers work out a little bit nicer. Okay, so beautiful thing is that uniform density says you have some flexibility. And in particular, because it has uniform density, we can slice in two different ways. So in other words, we could slice vertically or we could slice horizontally. Either is perfectly fine. Is there one that makes sense? Well, if you think about the way the problem has been written, you see it has x as a function of y. That's suggesting horizontal slicing. So we're integrating where it's the y that varies. There is something else that suggests horizontal slicing. Let's take a look at our picture. As we go from the bottom to the top, if we do horizontal slicing, you'll notice on the left-hand side, it's always this parabola, and on the right-hand side, it's always the line, which means you have consistency in your bounding curves. On the other hand, if you were to go vertical, you'd see that below 0, we're going from a part of the parabola to a different part of the parabola. After 0, we're going between a parabola and a line, which means that if we were to integrate this with respect to x, we'd have to do 2 integrals instead of 1. And it turns out that 2 integrals is twice as much as 1. We don't want to do more work. The more work we do, the longer it takes, plus we expose ourselves to the chance of making an integral error. So we want to minimize the number of integrals. So we have a plan. So we're going to horizontal slice. Or if you like, another way to say this is we're going to integrate with respect to y. Whoops, horizontal slice. So with respect to y. Okay, so let's just keep that in mind. We'll mark our curves here. Our parabola, we're already told it's y squared minus y. Here we have x equals y. And we can even spot, they gave us a grid here, let's make use of it. We see that we're at the origin 0, 0, and it looks like we're also at the point 2, 2, right? Because I'm going over 2, up 2. Let's just make sure it works. Does 2 equal 2? Yeah, it does. Does 2 squared minus 2 equal 2? And the answer is yeah, it does. So using the grid, we see it looks like 2, 2. Checking the formulas, it is 2, 2. In other words, the formulas are satisfied. Good. Good. All right. Well, now what? Okay. Well, our next thing to do is to look at this and say, what should we do? Well, we need to find x bar and y bar. Do we have any symmetry? No. Our shape is not symmetric, which means we are going to do 3 integrals. Oh boy, this will be fun. All right, well, we're patient people. We'll be okay. So we need to find x bar, which is our moment with respect to y over m. We need to find y bar, which is our moment with respect to x over m. So let's start with m. That shows up in both. Probably that's an important integral to do. So m is going to be integral start to finish. And what do you have? Well, you have your density. I'm just going to abbreviate. You have your area, right? And I'm going to, usually we say height times width. Well, because we're slicing in a horizontal way, I'm going to say width times height. Okay. My abbreviation for height is probably just as long as if I just spelled out the word height. Okay, all right. Well, you know where I'm going with this. So what do we have? Well, we know where we start and finish. We start at 0 and at 2. So we're going from 0 to 2. Our density is 2. Our width is between the two curves. So that would be high minus low, right minus left. So y minus y squared minus y. That's our width. And our height is this little thickness here, right? So our height is our change in y. That's our dy. So this becomes the integral 0 to 2. And the 2 is a constant. And here it becomes 2y minus y squared. Well, so this is 2. And then there's 2/3. Whoops. Sorry. Be careful here. That's mixing things up. So it's 2. And then the integral y squared minus 1/3 y cubed from 0 up to 2. Now, plug in 0, you get 0. Plug in 2. Well, you're going to get 4 minus 8/3. Now 4 is another way of saying 12/3. So it's 12/3 minus 8/3. 12/3 minus 8/3 is 4/3. Times that by 2 leaves us with 8/3. Okay, so that's our mass. Our mass is 8/3. So that goes here, 8/3, and there, 8/3. All right, now we go on to our moments. We're going to have 2 of them. Okay, so our first moment. Well, let's do, doesn't really matter which one, we'll do m sub y. So what is that going to be? Well, we're going to add up A to B, our location, our density, our width, and our height. So 0 to 2. Now, what we have to do is say, look, here's our middle. What is our distance to the y-axis? So what is this length? Well, whoops. Yeah. M sub y. I am sorry. That was m sub x. M sub y, that's this distance here to the y-axis. So this would normally, we would call it x. So what is that going to be? Well, our location here, we have to be very careful. I'm sorry. Going to be very cautious here. This is our x. And so for us, it would be equal to the y squared minus y plus y over 2. Right? Because what are you doing? Well, you average the left and the right. Y squared minus y plus y over 2. That's averaging left and right. So what is our location? Our location is 1/2 y squared. Our density is 2. Our width is same as before, 2y minus y squared. And our height is dy. Well, the half and the 2 cancel. So what do we end up with? It's the integral from 0 to 2. And multiply the y squared through. Okay, so the half and the 2 cancel. You have 2y cubed minus y to the 4th dy. So what is that? Well, you integrate. That'll be integral of 2y cubed. Well, that's 2y to the 4th over 4. So that's 1/2 y to the 4th. Here, 1/5 y to the 5th. From 0 to 2. Well, plug in 2. 2 to the 4th is 16 times a half. That's 8. And now, plug in here. 2 to the 5th is 32. So, 32 fifths. Well, 8 is 40 fifths. Subtract 32 fifths. Leaves us with 8 fifths. So, that's m sub y. Which means this part is 8 fifths. Okay, we'll come back and clean up later. M sub x. Now we need to do that computation. So m sub x is adding up a to b. Again, it's our location, our density, our width, our height. Now, when we talk about m sub x, now we're doing this length right there. And that is the y value. So this is y. So this is really clean. So it's kind of, because we've switched, we can integrate with respect to x if we do our vertical slices, or we integrate with respect to y when we do our horizontal slices. So when we're doing our vertical slicing, m sub x is the one that gets tricky because of that. Sort of like the y, you have to sort of like, well, it's this and that. When you do the horizontal slicing, it's the m sub y that gets tricky. But the other one's not so bad. So we're in the not so bad one. So everything else is actually the exact same as what we did for mass. So this makes it pretty straightforward, right? So integral 0 to 2, we have y, that's our location, 2 is our density, 2y minus y squared is our width, and our height is dy. So if you multiply this out, that's 0 to 2, and 2y times 2y is 4y squared. 2y times y squared is going to give us 2y cubed. Well, that would be 4/3 y cubed minus 1/2 y to the 4th. All right. Well, now we need to evaluate from 0 to 2. So we plug in 2. That'll be 4 times 8 over 3. So that's 32 over 3. And here, plug in 2. That'll be 16. 2 to the 4th is 16 over 2 is 8. Okay, so minus 8. Well, 32 over 3 minus 8, that's 24 over 3. Well, if you take 24 over 3, that'll leave us with simply 8 over 3 in the end. Okay, so 32 thirds minus 24 thirds is 8 thirds. All right, so that's 8 thirds. Well, now, what do you do? Well, you clean it up. We've done the integrals, and the last thing is just to say, well, hey, things like, for example, y bar. 8 thirds over 8 thirds is 1. That's great. Here, the 8's cancel. You bring that 3 up, and you say, well, hey, this is the same as 3/5. And so, putting this together, we get 3/5, 1. And that's the answer. So it turns out, according to this, well, 3/5, that's about 0.6. It's saying here, And we look at it and say, okay, is it reasonable? Well, is it roughly about, does it kind of feel like the center? Yeah, there's a lot of mass over on the left, there's a lot of mass on the right, there's a lot of mass above, there's a lot of mass below. So it's a reasonable answer. Probably even better, it's right. So good. Well, this is nice. We can switch, by the way, between horizontal slicing and vertical slicing. We don't have to memorize a whole bunch of different formulas. We just have to remember, hey, we have our generic, what are our pieces consisting of? And now let's just translate back and forth. The hardest part is just thinking about how do you figure out location. So if you're doing a small slice, you always say, look, my location is exactly in the middle. And now, if I'm doing location down to the x-axis, it's whatever the y value should be. And you say, am I integrating with respect to y or with respect to x? Because then you say, if I'm integrating with respect to y, well, it's just y. I'm integrating with respect to x. Okay, well, what is that y value in terms of x? If I'm looking for distance over here, over the y-axis, it's the x. Okay, well, if I'm integrating with respect to x, then that's it. I'm integrating with respect to y, I say, okay, well, what is it in terms of y? You have to think about these things. But if you're patient, you're careful, it works out. Okay, well, that's certainly a lot for us to think about for today. A lot of good practice. Thanks for coming and working through the problems. See you again.